Hello, everyone. I'm happy to see you here at the Research Festival. In this presentation, I will propose a reinforcement learning framework for autonomous driving. In this presentation, I will first talk about the algorithm we used. Then I will talk about the simulator CAT, the experiment we did using this simulator, and finally, I will talk about the future work and the conclusion. We proposed the autonomous driving problem as a discrete action Markov decision problem. In this project, we assume that all sensor data were well received and well processed. We focus on what policy the higher level decision maker should have to achieve safe driving and eco driving. So the transition probability and the reward function are used to specify the dynamics of the Markov decision process. They are specified as the first two equations. We also have a value function that maps a state to a real number. In RL setting, the value is usually the expected reward the agent could get given policy path. Also, the value function and the optimal value function are denoted as equations 3 and 4. Similar to value function of a state, we also have a value function of a state action pair, which is known as the Q function. Q function is basically the conditional expectation of the reward given a state and the action. In fact, it is important to find a good approximation of the value functions in order to let the agent to make good choices based on the good approximation of V and Q. In the next part, I will talk about how to have a good approximation of these value functions. In this project, we use a neural network as the function approximator for the Q function. Our neural network has 3 hidden layers with 10 neurons for each layer, and the layers are fully connected to each other. Each neuron in the output layer outputs the Q value corresponding to each action. Then I will talk about the training algorithm for the neural network. The algorithm of the DQN training is shown here. We first initialize the networks, and then we start training using epsilon greedy as our exploration method. During each time step, we pick an action, we execute the action, and we get the next state and the reward. We then store the tuple into our replay buffer. During each time step, we sample a mini batch of these tuples from the replay buffer, and we use those for our loss function and use the stochastic gradient descent to train our network. Finally, we update the target network for every n steps. Another algorithm that I have used is the enhanced policy iteration. The main difference between enhanced policy iteration and policy iteration is that they solve an optimal stopping problem instead of doing linear programming at the policy evaluation phase. Instead of only considering Q, the mapping F takes both Q and V into consideration. In the paper, they also prove that the map F is a supreme norm contraction, which makes Q star guaranteed using this mapping QK plus 1 equals to FQK. The algorithm of enhanced policy iteration is similar to the algorithm of DQN. The main difference is this update function for Q. It follows the mapping F I previously mentioned. In order to monitor and display the training process easily, we created the simulator software under Python 3. Its name is CAT for short. In the simulator, we have an infinite road that serves as the environment. We also have an OpenAI Dream style interface for training, the code for display and training. Next, we talk about the infinite road model. We have an infinite road for 5 lanes. The road has multiple rule-based cars and our agent car. The rule-based vehicles follows hand-coded traffic rules, and the state contains a tuple of 5 things. The VT and AT here are the current speed and current acceleration of our agent. The DFT and the VFT is the distance and the velocity to the front car. The FT here is the fuel consumption at time step t. The agent has to make one of the 5 choices for the action. And the reward the agent car gets is basically the distance covered minus the fuel consumption minus the punishment the agent gets if it collides or if it drives too fast or too slow on the road. These are the plots for the reward versus episode with DQN and enhanced policy iteration training. I chose to let epsilon decrease linearly with time. And we can see that in both plots, there is an upward trend of the average reward over time. However, it seems like there is a larger variance in reward in enhanced policy iteration. The reason might be choosing a uniform distribution in mu for the mapping F is not very good in our setting. This video shows the effect of training. We can see that the cars acts very randomly before the training. We can observe the randomness by looking at the accelerator here. The car doesn't know whether it should accelerate or deaccelerate. And the car can behave much better after training. We can see that the car brakes when it knows it needs to, and it always accelerates while it can accelerate. And the car can drive more than 1,000 meters in one episode, and it can get a positive reward as compared to the negative reward and the small final travel distance. Although we can get a good agent performance in our current setting, we can try more things. The first thing we can try is to use other exploration methods to balance the exploration and exploitation. We can use UCB or bottom-line exploration as our method to boost the efficiency. Second, we can use other RL algorithms like policy gradient methods. The third thing we can try is the multi-agent setting. I'm very curious to see whether the cars can collaborate with each other and get a higher result. Finally, I want to thank James, Garth, and Hal for being good teammates in the development of this brilliant simulator cat. I also want to thank you guys for listening.